So now it's a pleasure to introduce the first of this morning's plenary speakers. His name is Yurii Vlasov from the IBM Thomas J. Watson Research Center. For over 12 years, Dr. Vlasov led the development of silicon nanophotonics technology at IBM. He served as a company-wide strategist focused on the long-term vision of nanophotonics, aligned with the IBM Product Division roadmap. He's a fellow of both the Optical Society of America and the American Physical Society, as well as a senior member of the IEEE. His title this morning is Silicon Integrated Nanophotonics, from Fundamental Science to Manufacturable Technology. Let's give a warm welcome to Yurii Vlasov.
Thank you very much for introduction. Good morning, everyone. It's a great pleasure to present results of almost more than a decade of work of our department here at this conference. And obviously, I'll be focusing on silicon photonics, which is a very hot topic today, with a lot of interest from many companies, from many universities and academia alike. But what is interesting is to look on this kind of a history, which you see here on the slide, which also showing you that to some extent it's some kind of a deja vu, because these figures like that were very popular in the mid-'80s when silicon photonics was ramping up, and in principle all the ideas as well as inspirations were already formulated at that time. We are just repeating the same type of work that was done there, including this inspirational super chip that was introduced in '87 by Richard Soroff and Lorenzo, a very famous one, where people were trying to produce some kind of a vision where silicon photonics can go. And the idea is to combine optical and electrical signals together on one single substrate, which is silicon in this case, together with the electrical components like transistors. It's not a CMOS, it's BGT at that time. And then we have a super chip which combine both worlds together, and we can do optical communication like that seamlessly. What is also interesting, and that was very amusing for me to find this paper, which is a review paper, which is published in '87, which is saying the following, that during the last 2 decades, there is a lot of progress done in integrated optics based on silicon. So really, it has a very long history. It has a very deep roots. The question is why it's so popular today. Why it's such a hot topic? Why almost every big or small company that in microelectronics or in optical communications, they are dealing with silicon photonics in one or other way. And there are several products that are coming and already came to the market. And there is a huge hope that it will solve many problems in the world. So that's exactly the questions that I'm trying to address here. And I'll go through the topics one by one. So the first one is why silicon photonics is so popular. And especially if you assume that it's not only interest from academia, there's a huge interest from industry. So overall, it's about $1.5 billion so far invested recently for the last decade in development of silicon photonics. So one of the major reasons, as far as I can tell, is the new demand for optics, huge demand, which is coming from the change in IT industry in general and in our lives in particular. It's appearance of the cloud. So almost all computation from consumer electronics like iPads, iPhones, and everything, they are going to the big data centers. And enterprises are also shifting most of their computing powers outside. They're outsourcing it to big data centers. And this is just a map from Google showing where these data centers are located. They're all over the world. They're forming the backbone of our society today. If you look on one of them, this recently built Facebook data center in Iowa, it's a huge building. It occupies about 1.5 million square feet. Just for comparison, Super Bowl that happened a week ago, the football stadium there, the footage of it is about 100,000 square feet. This is 1.5 million square feet. That's how big it is. It's a huge building. It needs its own power supply, like 65 megawatt to power it up. But that's where all the Facebook operations are going when you are dialing on your laptop or on your iPhone or something like that. And if you look on what is happening there, how this is provided, it's provided by communications from iPhone to the tower to the network and then back into the data center. So from Cisco Global Cloud Index, it's tracking what is the total amount of data that is going all over the world that is supporting this cloud. So today it is about 2.6 zettabytes, and it is expected that it will be growing, and it will be growing very fast. By 2017, it's 7.7 zettabytes. It's enormous amount of data. I couldn't comprehend it. It's 1 billion terabytes, if you wish. But the thing is, if you look what is coming out of the data center, it's only a few pipes. So from all this building, these are the cables coming out. So it constitutes only 25% of all the zettabyte data, zettabyte traffic. So almost 75% of all this expected traffic, and what is happening today also, is inside this building, inside this data center. And if you look inside, that's one of the IBM's data centers. IBM is also playing this game. You see the racks of computer racks with the blades in there. They're all connected with their cables. In this case, it's electrical cables. You see the blades are connected by the cables, and each and every machine in the floor connected together. It's a very parallel system. So all this communication is happening inside the data center in these cables, in this network that is built inside. And the reason is very simple. It's all, in some sense, is inherited from their initial architecture, how it was invented by von Neumann. It's a communication between processor and memory. That's how all our computers are working. That's how this big, massive, gigantic supercomputer, if you wish, as a data center is working also. In order to have efficient calculations, in order to provide, for example, answer to your Google search, it's not one processor that is going through the cranking through the data. It's not two processors on a blade. It's not even one rack. It's a very parallel system. Your search is distributed in all their data centers and collected back. So communication is a bottleneck. And in order to connect these distant racks together, with distances of the order of several kilometers can be with these big, huge buildings, it is important to have very fast communication, and it's important to have very wide bus that is providing communication at this level of zettabytes or the like. So that's really an opportunity for optical communications, because now electrical cables couldn't provide this long reaches, more than 10 meters. It's already very prohibitive for data rates like 25 gigabit per second. So optics is coming in today, and that's what's happening now. So if you look, but at the same time, it's a new reality for optoelectronics industry. So for a long time, optoelectronics industry was mainly providing products to telecom type of communications, long distance, where their volumes are relatively small. It's about 10,000, maybe 100,000 parts per year for the whole world. And there are large margins. So we are talking about systems that can be sold for 100,000 or of the order of this type of money. Now we are talking about a completely different market. It's a market where the volumes are enormous. So for one data center like that, for one supercomputer, high-performance computing systems that IBM is building, it's about several millions of parts. So it constitutes a volume which is equal to the whole volume of all optoelectronics industry for a year. And this is growing. That's what is needed. At the same time, the price pressure is much higher, because now we are not talking about 100,000 multiplied by 6 million. You understand how much money you need to spend using existing products and existing technology. So it's impossible. It's prohibitive. So we are talking about hundreds of dollars, not really 100, but hundreds of this order. So we are talking about a completely different market, which optoelectronics industry have to adjust to, because that's our completely different rules of the game, and for that it's necessary also to develop new technologies. That is the major reason why there is such a big investment in silicon photonics. And you can see, actually, if optics is coming to their supercomputers. In this case, it's like a high-end data center. It's one of their fastest computers in the world. It's built by IBM. You see these cables, this yellow cables. These are optical cables. In this case, it's a kind of a traditional technology based on VCSEL multimode optics, because the size of this A supercomputer is not as big. The largest distances are of the order of 80 meters that can be covered by multi-mode VCSEL-based optics. Data centers that I was showing you before, with 1 million square feet, VCSELs multi-mode optics couldn't provide the distances. The reach is maybe extended, can be to 100 meters, but that is it. And after that, there's a big gap in terms of the technologies that can cover the regions from 100 meters to, let me say, 2 kilometers. So that's now an opportunity for single-mode optics. And existing single-mode optics is extremely expensive. So that's where we believe the silicon photonics has a play, and very important play. And this is the image that I made for our press release in 2012, when we announced to the world that IBM has developed this technology. It is based on standard CMOS. It's incorporating optical components and electrical components in the same stack as the transistors. And this technology is verified in the fab. So with that, I'll go through some historical development along this way, because it really took about almost more than 10 years, actually, to develop it, starting from early days of this project, somewhere in 2001, when I started it at IBM, when the idea was to explore fundamental science, whether we can do interesting physics in silicon, can we actually build structures in silicon, and can we shrink the size of the structures to something that is close or at the diffractional limit, to the fundamental limit of the scaling of optics. And we passed a long way through that. We published several papers along this way. This is just 2 of them showing that we can produce the structures and fabricate them with the standard CMOS technology, because we have a good control over the dimensions. What is interesting is that we can shrink the mode size to something like diffraction limit. You can make very tiny structures and observe very interesting physical phenomena, like slowing down the light here, or making a buffer out of 200 rings like that. Along this way, we also developed some understanding that maybe we can also connect these 2 worlds of electronics and optics, and can manipulate optical properties in such kind of nanophotonic waveguides at the diffraction limit with electrical injection in this case. So it's what you see on the top, it's a silicon waveguide, nanophotonic waveguide, where the mode is confined to diffraction limit. And we can inject carriers to modulate it, and by this way we can make an efficient modulator. So on the other side of the link, we need a detector. So this is germanium, which is not transparent at 1.3, 1.5 micron of interest, so we can absorb light. Once again, here the idea was initially to demonstrate the limits of optics, so to confine the light and to make a single-mode optical waveguide photodetector with germanium as thin as 100 nanometers. So in order to produce that, to achieve this goal, we developed a special technology how to grow germanium on insulator and then anneal it and have a direct crystallization anneal. It was very extensive work in this direction, governed directly by the idea, let's make it as small as possible. And it was a very interesting demonstration at the end. Also, what I want to say is that in all this years of exploratory work, of scientific exploration around this idea of building tiny diffraction limited structures on silicon, almost none of initial motivations were proved to be right. But it was a very important stage of development, because we started understanding what are the limits, we started understanding what is possible. And at that time, it became clear that maybe we developed something interesting for applications, because along the way, what we developed also is a set of additional processing modules that allow us to build these particular structures, which are important for communications, like modulator and photodetector, right next to transistors. So what is shown here is a flowchart diagram for the standard front-end integration of transistors in standard CMOS technology, starting from the shallow trench isolation, going to gate formation, anneal, and ending with the first copper interconnect level. What we developed along these years of scientific exploration are special modules that can be introduced almost seamlessly into the standard fab that allow us to build side by side with transistors also modulators, photodetectors, and coupling structures. And then, if that is possible, then, and we demonstrated several kind of demonstrations along the way that is showing that it's possible to integrate. It's possible to build optics right next to electronics, combine them together, And now it's becoming interesting as a technology. So at that stage, it has been decided that it's no longer prototype technology. Let's move it further. Let's move it now to from the lab in Yorktown, from the exploratory fabrication lines that is in our building over there, to the real mass production fab in this case in IBM Burlington. As there were many people involved in this transition, and it took a huge effort to go through that. One thing is to demonstrate the best ever device out of 20 wafers that still survive going through your exploratory lab, and another to put it in the mass-produced foundry with volumes of the order of 500,000 wafer starts per year. That's a completely different story, and that's what we are doing since. And the idea was other possible product implementation of that, because obviously it's required a lot of money, a lot of resources to go from exploratory stage, scientific exploratory stage, now scale up the project to move to a production. The idea was to build something like that, with a single die transceiver, which can provide up to several terabits per second communication, which is a parallel optics, which can be multiplexed using WDM. And it consists of both optical components and electrical components integrated on the same die. The advantage is obvious. I mean, we are decreasing the bill of material. If you open the current transceivers which are based on traditional technology, you will see about 30, 40 different components from different vendors that are packed together, that are packaged with more or less hand labor involved, and this constitutes a big portion of the cost of the whole solution. Here, the idea of integration, idea is obvious. If you integrate it all in silicon using the microelectronics industry approach with mass production, we can decrease the bill of material significantly. And we can integrate not only analog amplifiers that is needed here, but also digital circuitry maybe to augment communication, to restore the signal. And we also, what is important, can put the digital content in terms of microcontrollers and state machines and the like. So by this way, we can move many electrical circuits from the ASIC, from the computer chip, which is supposed to be right next to our transceiver, now to technologies that can accommodate this and can be cheaper, much cheaper, and not occupying a big area on the ASICs or high-performance computer chips. So there are advantages, obviously. Here, that was a vision, so we went through it. And the advantage of technology as we developed it, since we started from the idea of nanophotonics exploration, can we make the things as small as possible in optics, we end up in technologies that are scalable. So what you see here is a comparison back-to-back of our WDM device with our competitors. And you see that we are talking, in this case, it's actually a grating, and it occupies a very small area. And we are working already kind of at the diffraction limit. So this kind of ideas came up to this graph, which just illustrating what are the trade-offs. Because now the question is, which technology you want to put these different modules and build this new silicon nanophotonics technology on. We have at IBM range of technologies, from old ones like 150 nanometers, 150 microns, 150 nanometers to the latest technologies like 15 nanometers and 8 nanometers and the like. So the question is where to endorse it, where to put it in. And on one side, you want to have as fast electronics as possible. This gives the highest possible performance in optics also. But at the same time, there is a penalty you have to pay in terms of the development cost in new technology is much higher. And also just the max set is increasing exponentially in price when you are going from 150 to 8 nanometers or the like. So there is some trade-off here from economics, which you want to get a product that is as cheap as possible. At the same time, not to get performance, you want to get as far to the right in this graph as possible. And that's the trade-off between optical scaling and electrical scaling. In optics, we believe that we are at the limit. So going further into the next generation of technology will not give us much of an advantage in terms of the area on this chip. The performance of optics will be a little bit better because it's better control of the critical dimensions and roughness and all the like. But in principle, we are kind of good with this performance already. So 90 nanometer probably is the first technology you want to jump in this sense. From the electrical standpoint, we want to provide 25 gigabit per second per channel. That is where we see most of the volumes coming, not yet, but it will come. And that's what we are targeting, and that probably will stay there for quite some time. So in principle, the idea was to jump on the first technology that can provide electrically 25 gigabit per second. And then it is somewhere between 90 and 65 nanometers, relatively old technologies, but for this particular application, that's probably the best in terms of economics. Also, there was a choice of the substrate. So in Burlington, 90 nanometer was introduced first. It was one of the first 90 nanometers in the industry, and it was a bulk technology. It was developed for high-performance computing. It's very fast. It's much faster than anything else, but it's bulk. In optics, we need SOI, no matter what. We need to isolate the optical mode and silicon layer from the substrate. However, the thickness of SOI in our case is not a standard SOI for 90 nanometers, so it's something in between. It's some hybrid technology that should be ported into non-standard SOI. And that is kind of what we end up with, is to take bulk technology, 90 nanometer, as a base, move it to non-standard SOI, because in terms of the electrical performance, it's almost close. It will give us some boost in FTF max and the frequency of modulation. And there are many other advantages like with that. And that's what we've done for the last, I would say, 5-6 years. And the technology, once it's been introduced into the fab, it's going through the stages. It's a standard pathway for any microelectronics technology in the industry. It's going through stages of qualification. The first one is starting with technology feasibility. That's a stage of the order of like 1 year, maybe 1 year and a half, or maybe 2, depending on the complexity of the new modules that you introduce, of the amount of destruction to the base technologies that are coming with these modules. Because you can imagine that introducing these additional modules, in principle, I said it's seamless, but in reality, you do introduce additional things to the very well-tuned and oiled line, so it's necessary to requalify the electrical circuits to show that it's possible with all these additional new materials like germanium still to produce meaningful performance in electrical circuits. That was the first stage. Then it came the technology evaluation. Now we have vehicles like specially designed electrical circuits and optical circuits that are aimed at showing that it's not only possible to build all this stuff together, but when you build them, they can work. You can estimate when they are failing, what is their reliability. It's not just you can manufacture it, but now the question is, can you manufacture it and they will not fail most of the time, 99.9% or even more. And the third phase that we are in now, at the very last stage of it, it's a yield. That's an important parameter for technologies like that. That's kind of a major parameter for microelectronics industry, and that's probably the most difficult part to go through. So with this development, when we move everything to the fab, it's no longer the question of publishing, sound papers in famous journals, but it's with the best, device you have from many others that are failing, and showing one record performance, like how fast the modulator is modulating light. But really, you need to start looking on it as an engineering problem. You need the device that will fit into very specific parameter space for specific product. So that is no longer one heroic effort in one direction. This is optimization, multi-parameter optimization. Specifically for modulator, you can see there kind of a chart here, and the idea is that in silicon modulator, you can directly trade, for example, extinction ratio of your modulator with the losses that the light is encountering when it's being modulated. So in principle, you are affecting directly the optical link budget when you are starting looking at how deep your modulation is. So it's a direct trade-off. It's a direct trade-off also with the size of the modulator, so corresponding what is the area on the chip it occupies, and voltage that can be provided. Since we are talking about monolithically integrated optics, so voltage is fixed by technologies. It's 1.2 volts. We couldn't go higher. That's already kind of limits all these trade-off parameters, and that is very, very difficult and very extended engineering problems that we still are going through, but that is just completely different from the previous years of development that I was talking about. So we end up in the modulator, which in principle looks very similar to what I showed you before, but at the same time it's optimized based on all this parameter space that I was talking about. In this case, it's an interdigitated PN junction modulator with the idea to optimize charge per unit length, because in principle that's what you want. You want to inject and extract charges as fast as possible, as much charges injected or extracted in the unit length of the waveguide as possible. At the same time, to minimize the losses due to doping and other effects, and that's what we end up with. And since we are embedding this modulator in the standard CMOS with 9 layers of metals on top of it, so in order to make a traveling wave modulator that is known in the industry for a long time, now we have a big space for exploration to align the speed of the wave in waveguide, optical wave, and speed of the wave in electrical lines that are going and traveling together. Since we have very thick metals, this gives you big opportunity to make a lot of innovations now in making these traveling waves. And this is just one of them, recently published, I guess. Yeah, it's already published last year. Although this idea came very early on, the idea was how to actually make modulators much smaller. Because now you have traveling wave, you need to run for long distances in order to acquire 5 phase shift. Can you do it in much smaller footprint? And here the idea is to have a distributed modulator, where arm of the modulator is not as connected transmission line, it's separated into chunks. And at the end of each transmission, sub-transmission line, subcomponent of this arm, you have an inductor. That is something that is impossible to do with any other technology. Here it's for free. We have 9 levels of metal, we can build an inductor, and we can now delay the electrical light, we can impedance mismatch, the impedance matching the electrical and optical waves together, doing this kind of stuff. And it produced very good results. In reality, when you're going through all this math and all this multi-parameter optimization for specific product development, you see that probably small is not as important. Because at the end, the area on the chip, especially in such technology like 90 nanometer, is a commodity. It's not a big part of the final cost. The most important is to produce the performance that is needed. So we end up with this type of modulator. Most of this work is done by the colleague of mine, Doug Gale. So it's his great effort that went into this development. You see here it's a standard Mach-Zehnder interferometer, except that now we have segmented also structures without inductors. So we are giving up on this idea, but it's a little bit bigger in order to make a footprint smaller. So we have this wavering, path of both waveguides, electrical and optical, just to confine it to a smaller footprint. It produced very good results, but actually the latest development here, which is not yet published, is showing the straight waveguide. It's one-section waveguide. We're returning back to ideas known in 3.5 community for a long time. It's a little bit bigger footprint, but it's the best so far we see in all this optimization problem for modulation depth, for extinction ratio, for voltage that we need to provide, and for the losses that light is encountering when it's going through. It can go very fast to 25 to 32 gigabit as expected. So the same type of a very extensive development went into the development of the photodetectors and receivers. So we started with the idea of having this single-mode germanium waveguide photodetector that is based also on metal semiconductor metal interface. We end up in something completely different at the same time with a lot of relevance to our initial ideas. So first, we just separated the contacts from the middle of the waveguide to the sides, just to avoid excessive loss on the metal. Second, we changed the depletion region. We started with metal semiconductor metal with very confined electrical field, which produced very interesting results, but it's not very well controlled. So we end up with PIN junction. And we also increase the width of the waveguide from something that provide single-mode propagation in germanium now to much wider that allow us to put PIN junction on top and correspondingly avoid the losses. So it does resemble the initial idea. So you see here from the top of the wafer, if you look down in the microscope, that's how the detector looked like before on the top, and now how it looks today. So it's much wider germanium layer, which on the bottom you see it's a reddish color plate, which is sitting on top of the silicon waveguide, so you're looking through. And there is crystallization window on the other side of the detector that directs crystallization and makes the germanium layer fully crystallized. So there was a lot of development also in this direction on co-optimization of electrical circuitry and optical circuitry together. And a lot of circuit development went into with optimization of germanium structure in order to provide a very high responsivity. This is one of the latest results showing up to 90%, 95% responsivity at 1.3 micron for our photodetector, and it produced good results in the output electrical eye. So all this development over 5 years or so end up in this process development kit. So any microelectronics technology in the foundry like IBM or others has a product development kit. It's a library of elements starting from electrical elements like transistors of this type or that type, ESD devices, many other additional devices like eFuse and others, and optical devices like modulators, detectors, waveguides, WDM structures that are developed side by side, that have models behind them based on the hardware extraction and corners in technology and in temperature. And also they can be viewed from the cadence environment exactly in the same way as electrical components. So the designer can take parts of this library, combine this together, and build the circuit out of it, and make a modeling and calculations of what is happening. So that is the reference design for 4-channel, 25 gigabit each, 100 gigabit transceiver, coarse WDM. You see here 4 modulators and photodetectors around. And it's very small, as we tried to make it. It is mass-produced. You see here the package, which consists of dies coming from one wafer. So we're talking about, several hundreds of those just coming from one single wafer. So it is mass production technology. So by integration of all these components together, we were able to decrease the bill of material. And it was a lot of innovation went into that, a lot of effort to qualify the technology. As I said, it's in last stage now, but it appeared to be that's not really solving the problem. Because if you look on the cost components that are coming into transceiver as a product, bill of material is only probably 1/3 of it. Another 1/3 is packaging, and yet another 1/3 is testing. So if we are not addressing this other two, all these innovations that built into this integrated, monolithically integrated photonics technology will not pay off, because we have to pay for packaging and testing. And that's why we realized it early. And the idea was now to try to avoid as much as possible active alignment, hand labor, and many parts in the packaging. And also to use monolithic integration as a way to test the structure before it is being packaged. That what is allowed for the first time in optoelectronics industry to reduce and address these two other parts of the cost structure, testing and packaging, using monolithic integration. So usually in microelectronics industry, the chips are packaged by pick-and-place machines, high productivity machines, with precision relatively small, like 10 micron or so, but they are high productivity, 10,000 parts per hour. Chips are tested before being packaged, and when they are packaged, they are flip-chipped. So they are going in the package like shown on the right, with the ball grid array on the bottom, heat sink on the top, and then if you are talking about our silicon photonics die, we can have access to the edge only with the light. So that was the development that we've done. What you see here is a probe station on the floor in the clean room, in the fab, that can test both electrical and optical properties on the wafer scale. It can test passive optical components like transmission losses in the waveguide or 3 dB couplers or the like. It can test DC electrical properties like, for example, here you can see a dark current in the photodetectors for all the wafers in the slot. The sample size, by the way, is enormous. So just from one wafer lot, we have about 10,000 diodes on 18 wafers. So the sample size, the volume of testing is unprecedented for any optoelectronics industry. So it's a JEDEC size of sample in Telcordia type of qualification cycle. So that allows us to have a very good confidence on the performance and also on the yield and reliability. So with that, we also can build a built-in self-test right next to your product design that can be tested on a wafer before the wafer is sent to the packaging. That helps. But what also helps is this idea that we are developing for the last maybe 5 years, and it's mostly coming from Timon Barovich and his team. He led this development up to now. There were no publications whatsoever, except last year there were 2 ECTC publications. Now at OFC there will be several publications we started to publish in what we achieved there. And the idea is simple. So instead of hand labor, we want to build transceiver on the pick-and-place machine like shown on the bottom. In IBM facility, IBM Bromont, it's at the border in Canada, right across the border. It's probably one of the biggest microelectronics packaging facilities in North America. And they're using machines like that, high productivity with 10-micron precision. But we need to build optical components, with nanophotonic components with the precision of alignment of the order of 1 micron. So a lot of innovation came in now how to use standard machines like that, but with very non-standard components like fibers, like lasers that can be packaged together in a seamless manner. So the first approach, I just briefly illustrate this, is very simple, very old technology. Let's make a V-groove. We can do V-grooves on silicon with high precision. We need to now expand the beam in silicon nanophotonic waveguide that will match their beam size and the phase in the fiber. For that, we need to develop new technologies and new processing that is compatible with the standard CMOS, that is not disrupting anything there. And that's what is developed here. We're using metamaterial approach, very kind of fancy word now, but that's what it is. It's a structure that allow us to expand the beam in a controllable way to delocalize the beam that will matching the beam in the optical fiber. We also developed technologies that allow us to align multi-fiber, in this case it's a fiber ribbon, in an automatic way, in a completely passive way. And that's what you see here. On the bottom you see the silicon structure, silicon chip. On the top it's an array of the fibers, and they are automatically aligned using pick-and-place machine I showed you. And on the right, you see the aligned structure with fiber ribbon, 12 fibers in parallel, aligned all together with very good precision. And the numbers we are getting so far are pretty promising. So insertion loss about 1.3 dB, and with very good PDL. Another approach here is based on adiabatic coupling. It's no longer bad coupling like fiber to the edge of the waveguide. It's now light is coming in parallel. So in this case, it's a polymer waveguide array that is on top of the silicon waveguides. And you see here, it's also some additional structures that are used to mechanically align them together and to avoid excessive misalignment when you're using plus minus 10 micron precision pick-and-place machine. This work is done in collaboration with our partners from Asahi Glass and Furukawa. And you see here, once again, alignment is done on the pick-and-place machine. Alignment is pretty good. The results are shown here. So with plus minus 10 micron precision, we can get to 1 or 2 micron misalignment at the end using these structures, and the insertion losses are controllable. Now lasers. What you see here on the left is a laser die with multi-channel waveguides, and it's flip-chipped. There are ball grid array on the bottom, and when the laser is going through the anneal, it's self-aligning itself because now there is a meniscus formed on the ball grid array, and it moves the laser to the position which is required. So with that, I'm coming to the slide. It's an evaluation board with all the technology built in. You see here the chip in the middle. It is flip-chipped, as we discussed. It is packaged in exactly the same way as microelectronics chips. At the edge, there are fibers. And with that, we have a technology now that can do that. Technology went through several stages of qualification, and it's very soon it will be ready for complete product. We have several partners using that. And with that, I probably will finish. Thank you.